Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. I'm Philip Emeagwali. In 1989, I was in the news for discovering that the slowest processors could be used to solve the biggest problems arising in mathematics and physics and find their answers at the fastest speeds. The fastest computer is why you know the weather before going outside. Briefly, my mathematical quest was to find how to solve the toughest problems that arise at the intersection of calculus and large-scale geophysical fluid dynamics, including solving the initial boundary value problems known as global climate modeling and petroleum reservoir simulation. As a research mathematician who came of age in the 1970s and 80s, who is at the frontier of physics and supercomputing, my grand challenge in those 2 decades was to be the first person to understand how to solve initial boundary value problems at the intersection of partial differential equations that are encoded in some laws of physics. My contribution to mathematics is this: I was the first large-scale computational physicist and the first person to solve initial boundary value problems across a new internet. My new knowledge of the world's fastest computer is used to understand the spread and treatment of COVID-19. I visualize my internet as a new global network of the slowest processors in the world. I theorized that my internet could be harnessed and used to execute the fastest computing in the world. For 16 years, following June 1974, and from Corvallis, Oregon, to Los Alamos, New Mexico, the naysayers forced me to conduct my fastest supercomputer research alone. In the early 1980s, I was often disinvited from giving supercomputing lectures, and only disinvited after they discovered that I was black and African. I invented the 9 Philip Emeagwali equations, and I did so from scratch, or first principles, called the second law of motion of physics. My system of 9 coupled nonlinear and time-dependent partial differential equations governs initial boundary value problems that must be used to model the subterranean motions of crude oil, injected water, and natural gas flowing up to 7.7 miles or 12.4 kilometers deep and flowing below the surface of the earth and within an oil-producing field that's often the size of Ibadan, Nigeria. The world's fastest computer is like a telescope that's used to peer inside the human DNA, or 7.7 miles deep inside an oil field. My quest was for new knowledge that will enable me to parallel process computational fluid dynamics codes used to model the weather of up to 7.7 miles or 12.4 kilometers below the surface of the earth. This grand challenge problem is the poster girl of compute-intensive physics. In 1989, I was in the news as the first person to discover how to divide the biggest problems in mathematics and physics and divide each grand challenge problem into up to 1 billion lesser challenging problems that can then be solved across as many processors or with a one problem to one processor correspondence. For my specific experiments across the world's slowest processors, in which I recorded the world's fastest computing and did so at 8:15 in the morning of July 4, 1989, I visualized my 65,536 equal reservoir models as oil field number 1, oil field number 2, all the way to oil field number 65,536. I visualized a one oil field to one processor correspondence. I executed that one-to-one mapping between those oil fields and as many processors that shared nothing. My processors were equal distances apart, and each processor operated its operating system. My processor-to-processor email directions were that oil field number 1 is directly and bidirectionally connected to oil field number 2. Oil field number 2 is directly and bidirectionally connected to oil field number 3. I continued to directly and bidirectionally connect all nearest oil fields. But the last, or oil field number 65,536, is directly and bidirectionally and circularly connected to oil field number 1. My one-to-one mapping was at the core of my discovery of the world's fastest computing as we know it today. I was in the news because I discovered how to hindcast the weather 8 miles inside the earth. The polymath knows more sciences than the mathematician and understands a priori that the calculus that governs the short-term weather below the surface of the earth have identical partial derivative terms as the calculus that governs the long-term weather above the surface of the earth. The reason for the mathematical similarity is that both are computational fluid dynamics problems grounded on the partial differential equation of calculus and on the partial difference equation of linear algebra, and in part because the dependent and independent variables are similar. Accurate weather forecasts are generated with supercomputers and are critical to protecting life and property. Back from September 1, 1981 through August 1986, I lived a 15-minute stroll from the Graymax Heliport building in Silver Spring, Maryland. The Graymax building was the then headquarters of the U.S. National Weather Service. During those 5 years, and from Mondays through Fridays, I stopped each morning and spent 5 hours with hydrologists and meteorologists. During my 5 years with those research meteorologists, I was inspired to look into the finite difference discretizations of the primitive equations of meteorology that were used by the U.S. National Weather Service and used to forecast the weather. In the early 1980s and in College Park, Maryland, I discovered that the grand challenge problems of hindcasting the weather underneath the earth and forecasting the weather above the earth are governed by initial boundary value problems that look similar, yet For a century, the geologist and the meteorologist was not aware of that similarity. That ignorance robbed both fields the benefit of cross-fertilizations of their discoveries. The computational fluid dynamics model that I executed across my ensemble of 65,536 processors was the most difficult problem in supercomputing. It was an initial boundary value problem posed across a new internet that I defined as a new global network of 65,536 processors that shared nothing. In the 1980s, the US government classified this problem as a grand challenge, and did so in part because its solution demands $1 billion supercomputer that occupies the footprint of a football field and that then existed only in the realm of science fiction. As a mathematician and physicist who grew over the 1970s and 80s to become the first programmer of the first supercomputer as it's known today and as it's expected to be known tomorrow, I know from first-hand experience that it was harder to solve an initial boundary value problem and solve it across millions of processors than to merely pose the problem on one blackboard. The former is the solution discovered by the polymath. The latter is the question asked by the mathematician. It's easier to ask a question than to answer it. As a mathematician searching for new calculus and new algebra, I looked for and made use of patterns and structures from disparate fields of human knowledge. A few years ago, I posed a question meant for the Joint Admissions and Matriculation Board of Nigeria, or JAMB for short. What is the importance of physics in the development of Nigeria? The supercomputer must be used to tackle the biggest and the most difficult problems of tomorrow. In the 1980s, the precursor to the world's fastest computer was confined to crunching massive amounts of data from large-scale computational fluid dynamics simulations. My computational physics across millions of processors must be used to locate energy deposits. Please allow me to quote myself from a lecture that I delivered in the 1980s. In petroleum reservoir simulations executed for the oil fields of Nigeria, the dependent variables are the compressibility of the fluids, pressure, fluid partial molar volume, saturation, phase partial molar volume, total fluid velocity, as well as source and sink terms. Such terms include water injection wells and crude oil and natural gas producing wells. To derive the system of equations of extreme scale computational linear algebra within compositional reservoir simulators used for enhanced oil recovery processes that must be parallel processed across an ensemble of processors demands that the governing system of coupled nonlinear time-dependent and three-dimensional partial differential equations be discretized with one of three finite difference techniques. The first technique is known as the implicit pressure explicit composition method. This finite difference approximation has small time steps and the least computation time per time step. The second technique is known as the implicit pressure and saturation method. This finite difference approximation is more stable and handles larger time steps. The third technique is known as the fully implicit method. This finite difference approximation is the most stable and handles the largest time steps. I became a supercomputer scientist after putting in my time in grade. My due diligence that yielded the world's fastest computing occurred daily, and it occurred during my half-century of supercomputing that was onward of June 20, 1974 in Corvallis, Oregon, USA. I'm the subject of school essays because I was the first person to figure out how to solve the most difficult problems at the crossroad where new mathematics, new physics, and the world's fastest computing intersected. Such grand challenge problems could only be solved on supercomputers if and only if the number of processors harnessed is sufficiently large. What's the importance of supercomputers to Nigeria? A Nigeria without supercomputing is a Nigeria with reduced petroleum revenue. In retrospect, the world's fastest computer suffered from the cause of rising expectations. The unorthodox supercomputer of 1989 that had only myself as its only full-time programmer reset itself to become the conventional user-friendly supercomputer that now has 1,000 simultaneous users. The grand challenge problem of supercomputing is a tough question that the petroleum industry must answer. Their answer must lift the common citizen in Nigeria from poverty. The answer must be grounded several miles deep inside the oil fields of the Niger Delta region of southern Nigeria. That oil field covers the area the size of a town. In Nigeria, extreme-scale petroleum reservoir simulators are used to discover and recover otherwise elusive crude oil and natural gas. On the 4th of July, 1989, I became the first person to understand how to solve a grand challenge problem and how to solve it across a new ensemble of processors that surrounded a globe as a new internet, that's a new global network of processors. That was how I became the first person to figure out how to solve the grand challenge problem of supercomputing and how to solve it across a never before visualized internet that's a new spherical island of 1 binary million or 1 binary billion off-the-shelf processors that were coupled and which were equal distances apart and that shared nothing. The difference between each of the 25,000 vector supercomputer scientists of the 1970s and 80s and myself was this: I had the self-confidence to tackle the most difficult mathematical problems in supercomputing and to solve those once impossible problems alone, but only aided by my ensemble of 65,536 processors that computed in tandem. I visualized my new internet as encircling a globe in the manner the internet encircles the earth. In 1989, I was in the news as the mathematician that harnessed the first supercomputer as it's known today to solve such difficult problems. I solved them when every mathematician said that their mathematical solutions were impossible, even across an ensemble of 1 billion processors. At all science and for the grand challenge problems, I was cognizant of the fact that calculus and algebra were the two recurring decimals on my blackboard and motherboard, respectively. Prior to the parallel processing of my computational fluid dynamics problem, I had to discretize a system of governing partial differential equations of calculus called the primitive equations of weather forecasting. That was how I invented my finite difference algorithms of the algebra of weather forecasting. Those algorithms are the sets of computational steps or the floating point arithmetic operations that must be solved at the extreme scale algebraic core of the compute-intensive problem at the core of weather forecasting. That was how your evening weather forecast used the second law of motion of physics to predict the motions of atmospheric flows and compute dependent variables and present them as sequences of contoured fields. The remaining equations used in weather forecasting include the hypsometric equation that was derived from the hydrostatic equation and the ideal gas law. It also includes the thermodynamic energy equation, or the first law of thermodynamics, that states that the change in internal energy is equal to the heat added minus the work done, and the continuity equation. Often, the mathematical formulation of the primitive equations of weather forecasting yields a system of 5 equations with 5 dependent variables that include the fluid velocity relative to the rotating earth, the density, and the pressure. A supercomputer that sells for $1 billion is more complex than a novel that sells for $20. My contributions to science cannot be published in science journals that has page limits, nor can it be explained as a short-term memo to the White House. A memo can only convey a vague but not fully formed idea. The supercomputer or internet cannot be described within 6 pages or 1-hour lecture. For that reason, I described my contributions to the world's fastest computing. I did so across a series of 1,000 podcasts and YouTube videos. Writing my life story and contributions to the world's fastest computing, and doing so without dwelling on the 9 partial differential equations that I invented in the early 1980s, and while in College Park, Maryland, would be like producing the play Hamlet without the Prince of Denmark. I invented 9 new partial differential equations for mathematical and computational physics that are called the 9 Philip Emeagwali equations. The partial differential equation is the pinnacle of mathematical physics. The supercomputer is to the partial differential equation what the telescope is to astronomy. The new partial differential equations that I invented and that I figured out how to solve across the new internet that I invented was the cover story of top mathematics publications. Those publications include the May 1990 issue of the Siam News, published by the Society for Industrial and Applied Mathematics. My new partial differential equations made the news headlines because the new parallel processed mathematical computations which I executed across my new internet, that was a new global network of 65,536 processors, were science fiction to the community of research computational mathematicians of 1989. My contributions to mathematical knowledge were newsworthy because it was then impossible to parallel process and to solve at the fastest computer speeds the partial differential equations of extreme scale mathematical physics. The 9 partial differential equations which I invented were credited to me because they had never been scribbled across any blackboard or printed in any textbook or written in any known notebook. Because I invented those 9 partial differential equations, I knew them forward and backward and even sideways. For that reason, I delivered my mathematical lectures of the 1980s and now in prose and without notes or blackboards. Across YouTube, I'm the only mathematician that delivered his partial differential equations without PowerPoints. It was noted in YouTube commentaries that I was the only mathematician who delivered his mathematical lectures to leading mathematicians and delivered them in prose and poetry, and delivered original partial differential equations without notes. I delivered my new partial differential equations without notes, and I did so when other research computational mathematicians buried their faces on their blackboards, scribbled with partial differential equations and scribbled with companion partial difference equations, all borrowed from textbooks. Before February 1, 1922, theorized parallel processing existed as a blank sheet of paper or as science fiction. Before July 4, 1989, the parallel process solutions of the most compute-intensive problems only existed as science fiction. To discover that the fastest computer can be built with the slowest processors was news headlines because the invention shook the world of supercomputers. Before my experiment of July 4, 1989, that made the news headlines, the evidence that supported the technique and technology of parallel supercomputing was thin to non-existent. As a supercomputer scientist, my research quest was to invent the world's fastest computer and to invent how to compute across processors and compress times to solution of initial boundary value problems that arise when solving the most compute-intensive problems, such as global climate modeling to foresee long-term global warming. In 1989, I was in the news because I discovered how to compress the times to solution that was needed to solve the most compute-intensive problems in science, engineering, and medicine. My contributions to the development of the computer were these. I discovered how to compress the time needed to solve the most compute-intensive problems that were once impossible to solve, and how to solve them by sending and receiving emails and communicating along my new global network of 1,048,576 email wires. My initial boundary value problems of mathematical and computational physics were sent to and received from an ensemble of 65,536 coupled processors in which each processor operated its operating system and shared nothing between nearest neighboring processors. Parallel processing creates more eureka moments, such as in the world's fastest computer that harnesses 10.65 million off-the-shelf processors and uses those processors to solve the most compute-intensive problems. Within the world's fastest computer, parallel processing is the vital technology used to reduce the time to solution from 30,000 years or 10.65 million days of sequential processing on one central processing unit to merely 1 day of supercomputing across 10.65 million central processing units. In one form of the primitive equations, or the system of hyperbolic partial differential equations that governs the difficult mathematical problem of extreme scale weather forecasting, the dependent variables are the zonal velocity in the east to west direction that is tangent to the sphere, the meridional velocity in the north to south direction that is tangent to the sphere, the vertical velocity in isobaric coordinates, the precipitable water, the Exner function or non-dimensionalized pressure, the potential temperature, the gas constant, the pressure, the specific heat on a constant pressure surface, the heat flow per unit time per unit mass, the temperature, the geopotential, and the term for the Coriolis force. What separated the serial and the parallel paradigms of the world's fastest computing is not the difficulty of the problems they solved, but how they solved it. Your weather forecast was enabled by the parallel processed initial boundary value problem based on the primitive equations of meteorology. Each equation was a balanced equation that accounted for something, such as where fluids come from or go to, and how the total fluid changes in time and space. The first of the 6 primitive equations encode the law of conservation of mass. The second, third, and fourth partial differential equation of the primitive equations encodes the law of conservation of momentum. The fifth partial differential equation of the primitive equations expresses the relationship between the temperature to heat sources and sinks. The general circulation model is a climate model based on the general circulation of the Earth's atmosphere and oceans. The climate model is an ensemble of millions of parallel processed initial boundary value problems of calculus, each governed by the primitive equations of meteorology. This system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations encoded some laws of physics and chemistry. To parallel process the global climate model, the supercomputer scientist must chop up the extreme scale mathematical problem into millions of smaller three-dimensional models. Each small global climate model computes in tandem the wind speed, heat transfer, relative humidity, radiation, and surface hydrology within itself. And it must exchange boundary value data with the nearest neighboring global climate models that were executed within the as many processors. I discovered how to slice and dice grand challenge initial boundary value mathematical problems and massively parallel computing them in smaller chunks and aggregating them for the complete results. My discovery of the world's fastest computing across the world's slowest processors made the news headlines because it was a big step towards the invention of super-fast computers computing at the speed limit. The world's fastest computer costs 40% more than the mile-long Second Niger Bridge of Nigeria. Why are supercomputers important in climate modeling? the world's fastest computer, is used for the most detailed mathematical calculations, such as predicting long-term global warming. What is a world without supercomputers? The world's fastest computer is used to solve problems that did not exist before. The world's fastest computer costs $1,250 million, or the equivalent of 25,000 man-years, with each man paid $50,000 per year. For this reason, a full-time computer science instructor that conducts part-time research aided by only 3 20-year-old students cannot construct the world's fastest computer. A state-of-the-art computer is 1 billion times more powerful than the everyday computer. The fastest computer in the world is far more complex than the spacecraft that took men to the moon. The development of the most powerful computer demands up to 25,000 pairs of hands and as many brains. On the 4th of July 1989, I recorded the highest speed up and the fastest speed in supercomputing. That scientific discovery led to my conclusion that supercomputing across the slowest 1 billion processors could become the technology that can yield a factor of 1 billion fold reduction in the wall clock times of the most compute-intensive problems. Such grand challenge problems include global climate models that must be used to foresee otherwise unforeseeable long-term global warming. Without parallel supercomputing, it would take centuries to foresee climatic changes. What is the difference between the global climate model and the general circulation model? The general circulation model simulates the circulation of the atmosphere. A global climate model might be based on a general circulation model. The global climate model is used to predict what will happen in the Earth's climate in the coming centuries. The climate in London is the average weather in London for over 30 years. My mathematical contributions to the solution of the primitive equations used to forecast your evening weather were these. I discovered how to parallel process and compress the time needed to solve the grand challenge problem of weather forecasting that is an extreme-scale initial boundary value problem of computational physics. I discovered that with 10.65 million processes computing in parallel, that a time to solution of 10.65 million days or 30,000 years dropped to 1 day of time to solution across a new internet, that's a new spherical island of 10 binary million processors. Without parallel supercomputing, tomorrow's weather forecast will be issued 30,000 years later. A famous debate on the future of the parallel supercomputer took place between April 18 to 20, 1967, and at the Spring Joint Computer Conference in Atlantic City, New Jersey. After that debate, the consensus was that parallel supercomputing will forever remain an enormous waste of everybody's time. That debate was between IBM's Gene Amdahl, who opposed parallel supercomputing, and Daniel Slotnick, who proposed parallel supercomputing. Gene Amdahl, who designed the world's most successful single-processor computer, named IBM's System 360, won that debate, and his victory gave rise to the famed Amdahl's law that later entered into supercomputer textbooks. Amdahl's law decreed that it would be wasteful to design supercomputers that are powered by 8 or more processors. According to Amdahl's law, an infinite number of processors will be wasteful and will not yield an infinite increase in the speed of the parallel supercomputer. Amdahl's law was the reason fewer than 8 processors were incorporated into the supercomputers of the 1960s through 80s. On July 4, 1989, I discovered the new supercomputing knowledge of the world's fastest computing across the world's slowest processors. That contribution is the reason I'm the subject of school essays on computer history. On my blackboard, I use the most advanced expressions from the frontier of calculus and computational fluid dynamics. Those expressions are called partial differential equations. Partial differential equations are used to foresee the motions arising during plate tectonic, supernovas, and tornadoes. Partial differential equations are used to design superconducting magnets for superconducting supercolliders. Partial differential equations are used to design superconducting magnets for supercolliders. Partial differential equations are used to foresee the motions arising during plate tectonic, supernovas, and tornadoes. Partial differential equations are used to study the transport of ions across kidney membranes. An ion is an atom or molecule with a net electric charge arising from the loss or gain of electrons. But by far, the most important and the most frequently occurring partial differential equations are those that encode laws of physics, such as the conservation laws for matter, momentum, and energy, and chemical species. The laws of conservation are the common denominators in many initial boundary value problems, such as those arising in extreme scaled parallelized computational fluid dynamics, such as modeling the hurricanes and tornadoes to protect life and property, and the design of hypersonic aircraft, quiet submarines, and efficient automobile bodies. In the fluid dynamics of the Earth, the solutions of the governing partial differential equations are the mathematical descriptions of both the oceanic and the atmospheric flow patterns. That mathematical and computational solution is simply called short-term weather forecast, or the long-term global warming prediction. The formal mathematical name for this is initial boundary value problem. It's a boundary value problem because the Earth's surface is its lower boundary, while the Earth's upper atmosphere, that is 62 miles or 100 kilometers above the Earth's surface, is its upper boundary. The world's fastest computing is the key technology that must be used to address the grave existential threats of the 21st century. The biggest threat to life on Earth is to understand the abstract and seemingly invincible global climate change. We lack the visceral understanding of the urgency of global warming. In the long run, the proximity of the climate crisis is worse than any global pandemic and economic collapse we can imagine. Parallel supercomputing that was once confined to solving compute-intensive initial boundary value problems is now used to solve mathematical problems that arise across many industries. The world's fastest computers are used to foresee long-term global warming, reduce the energy crisis of the world, search for extraterrestrial intelligence, understand how living cells function, mark the human genome, kill diseases, and speed up the search for new antiviral drugs and for new vaccines with the least side effects. I invented the blueprint that's used to design the first supercomputer as it's known today and as it could be known tomorrow. My discovery, which occurred on July 4, 1989, opened the door to the world's fastest computers that compute across an ensemble of up to 1 billion processors. What happened in 1989 was that I invented something that was waiting for me. My contribution to the development of the computer is this. I was in the news for discovering that the world's fastest computers can be manufactured from standard parts known as off-the-shelf processors, including from the world's slowest processors. My supercomputer invention made the news headlines because it provided the answer to the most pressing question at the crossroad where mathematics, physics, and computing intersected. After my discovery, it became possible to simulate long-term global warming. I do so faster and across up to 1 billion processors. Today, the world's fastest computers are powered by up to 10 million processors. The reason is that 10 million processors powering a supercomputer makes it possible to obtain a more detailed and realistic global climate models that must be used to foresee century-long climate changes. Why is the fastest computing across the slowest processors a critical and enabling technology? And what is the contribution of Philip Emeagwali? My contribution to the development of the computer is this. I discovered how to populate the world's fastest computers with 1 billion processors that shared nothing but were in dialogue with each other. And I discovered how to solve the hardest problems and solve them by chopping them up into 1 billion smaller problems that can then be solved in tandem. I discovered that rapid fire speed, that's the first world's fastest computing to be executed across the world's slowest processors, and discovered it as modular. Therefore, the supercomputing technology can be repeated 1 billion-fold to gain as much speed increase. In a different perspective, if all our high-resolution, three-dimensional, and time-dependent computational fluid dynamic simulations we are represented by one uninterrupted simulation that's executed within one processor, then our pre-human ancestors who used the first stone tools may have had to start our supercomputing simulation and started it 3 million years ago so that we can have their answer today. That technological feat called for a civilization on Earth that pre-existed before humans. Thank you. I'm Philip Emeagwali. Thank you very much. Thank you.
Insightful and brilliant lecture.